Okay, so this is Dr. Carolyn A, and she's a distinguished professor at Rutgers University. She's the director of the Robert B. Davis Institute for Learning. She'll tell you a little bit about Robert B. Davis in a little bit, I'm sure. She's also the editor of the Journal of Mathematical Behavior. And she taught secondary and college mathematics, and her research focus is on looking at how students can build powerful mathematical ideas, how they enjoy doing mathematics, and how they engage in productive mathematical arguments, leading to proof-like justifications. She has over 25 years of data on video of collection of students doing mathematics, and that's part of her video Mosaic project, and that's what she's going to talk to us about today.
Okay, well, it's a pleasure to be here, and that you're interested in learning about a quarter of a century of work. Some of you are probably not that old. That's right. We're just close to that when this work began. But I'm really delighted to be here, and I have two parts to the presentation to focus on, but let me begin by giving you an outline of what I'd like to hope to accomplish today. I'm going to start from my most recent work and then maybe go backwards a little bit. So I'll go recently, what we've been doing, and then move back to currently we're using videos for teacher learning, teacher education for both pre-service and in-service teachers. We use videos as a tool for that learning. You'll see some examples of that tool. Give you a little brief history of our video collection and where it's housed in a repository built at Rutgers called the Video Mosaic Collaborative, VMC. You'll hear a lot about VMC. Collaborative repository stores our video, and new tools are being developed to work with video on the current NSF funding. One of the tools is the VMC Analytic. I'm going to talk about that tool. I'd like to give you an example of how that tool was used to tell video narrative by one of our students, and show you where you can find more if you'd like, and some of the affordances. Also, I'd like to tell you where we are in our current cyber learning grant to build other tools to work on the VMC that will enable folks who are working with video to do collaborate in social networking kind of environment. So suppose those of you were deciding in special ed, you wanted to trace how a student represented some of her early ideas in learning a particular math topic. Maybe three of you want to collaborate, and you can be building this VMC analytic together on the social networking tool. So great possibilities. I'm going to give you some results from a design research study. Some of this is being published in a paper that was just accepted and will be out who knows when, you know how that works. But if you're interested, I can send you the paper and share some videos from the VMC Analytic. And it was very interesting to know what some of you students are interested in that could make suggestions for what videos that I could share. So what about background and resources? Our research, like any kind of research like this, is not done in isolation. It's done really with lots of folks, and it's done in a way that we can say it takes a community to raise, right, a village to raise a child. It takes a community of collaborators to carry on projects like this. So I have lots of people I'm going to cite at the end. Don't let me forget to do that. I was very happy, to be leading a lot of this work over a quarter of a century, but again, there are many, many players and players, colleagues, graduate students, and so forth. So we'll talk about that. We have been working for over a quarter of a century, beginning with longitudinal study, following the same group of students from their first grade up until the present, which takes us to 25 years. And we are continuing that work, so those students are about 30, 31 years old. Anyone here younger than that? You get the picture, right? So we've been studying them a very long time. And we have collected over the years, not only from a longitudinal study, but cross-sectional studies. We have been, a longitudinal study comes from one particular school district, working class, blue collar district, but we've had cross-sectional studies in urban, affluent suburban, We've also had studies done in informal math learning after school. So we've had a variety of conditions for our studies over these years, and this is what makes up our database. The particular database gives us opportunities for attending to the details of students' mathematical learning, and also what our moves have been as teacher researcher. It's important to kind of keep in mind what I'm showing you. These were all research projects. These were not projects to show you how to teach something. It was to study how students learn and build up mathematical ideas and ways of reasoning. And so as researchers, we had to be very, very careful to not impose our own way of doing, our own way of thinking on the students and the subjects. You will be the judge of that. As you look at those clips, as you look at those videos, you will decide if that's what we're doing. And you will decide what kind of moves we make, what kind of questions we might ask, what might we call attention to. These are the kinds of things students study and make analytics about. These make great projects. By the way, if you make an analytic, you submit it to publication, I'm told it gets up there for about 50 to 100 years, and it's a really valid publication. And I really encourage you all in this room, everyone here, to think about doing that, or even writing a paper for a conference presentation that has as a basis an analytic you've created that can be published and referenced. There are really good opportunities here. And this is sort of another way, and a more efficient way of movement to publication, and where you actually have to back what you're saying with evidence. You have to provide the backing, the video evidence, and it's fun. I'm going to talk about teachers learning from videos, and this is what you need to write down in your little notebooks as you're taking notes. I'm going to come to this. This is the website, www.videomosaic.org. That's where our repository is housed, and we'll tell you how to navigate and how to go through it and how to use it. Any questions so far? Okay, so what is this all about? Well, we are all very much aware of the importance today of STEM education, right? And it's not just, mathematics education, it's mathematics, the sciences, engineering, and so forth. We're very all aware that we need to produce folks who are able to learn in these many fields and carry on and build knowledge. I'm told that the data suggests that we have fewer people pursuing STEM fields than we did maybe 10 years ago, and that surprised me, and at the same time saddens me. But how do you do this? I mean, the work that we've been doing and the work that I advocate has to do with the notion of when you're learning mathematics, you need to have meaning and deep understanding of the concepts. These are just not words. They have to be backed by meaning. They have to be backed by understanding. Now, I'm sure there's a person in this room that at some time in their educational career did something with mathematics that they didn't understand what they were doing. It must have happened to you at least once. The example I'll use, if you've taken a stat course, it's probably happened there for sure. Right? You say, computer standard deviation, and you talk about so many standard deviations, but you really understand what that means, really conceptually, meaningfully, and why that definition is being used rather than another way of looking at variability. Meaning, deep meaning is important. Collaborative learning is important. Collaborative learning is something we expect that is important lifelong. We don't make discoveries and do work by ourselves. My own work, I could speak, was because of a collaboration. I collaborated with colleagues, I collaborate with my students, collaborate with schools and partnerships. Collaboration is extremely important. We need to learn how to be good collaborators. That's extremely important in the mission of our work. Now this means we need to encourage discourse, meaningful discourse, and we need to encourage everyone to be able to communicate their ideas comfortably, without risk, without feeling that you're personally taking great risks in doing it. You have to be free to express your views and your opinions to profit from the communication and discourse. This is something that I assume. Reasoning and problem solving. You should be able to back your ideas with good arguments. You should be able to reason about them. You should be able to provide support. We don't hire people in fields today to solve problems that have already been solved. Okay? Wherever we go in work, you're never going to see the problem, any math problem you've been given in school, that they're going to ask you to solve in work. You're going to be challenged, no matter where you are in teaching and situations and some of the moves and changes, to solve new problems. And those new problems aren't going to have one way to solve. There are parameters, there are assumptions you make, right? You say, you might do this under these conditions, you might do this under these conditions, and so on and so forth. But this is what really your lifelong challenge is going to be, even if you're buying a house, right? Even if you're choosing where to live. All of these problems have certain parameters associated with it that's very important, and hopefully you're not going to make these decisions by yourself, you're going to collaborate with knowledgeable others. Agreed? So that's part of what we expect people in life to do, and so some of this, as you know, involves interdisciplinary work. I'm going to switch a little bit to really what I'd love to talk about is the Video Mosaic Collaborative. Okay? So what it really is, it's a place to store data. And the data we're storing is video data, and lots of it. It's called big data. Our own collection has over 4,500 hours of data. And in order to be stored, you just don't take the data and dump it in this repository. This is the work of really, again, collaboration and colleagues who have particular ways of storing data so that you can retrieve it, so you can search for it. And this is why we work with Rutgers Library and the digital library, the person in charge of the digital library, to prepare the storage of our data for the Video Mosaic Collaborative so that we can share it, so that you can search for it and you can find it efficiently. So in our repository, what we've done at this part of our work, there are other parts, but we've taken some video strands and we've taken videos that were maybe 1 hour and 15 minutes in length on average, because that's how long our classroom sessions were. When we did our research, we negotiated for long sessions for some of our problem solving, so we would have 2 long sessions and maybe a shorter session. And we partition this full video into clips. And so the 1 hour and 15 video might be talking about students dealing with equivalent fractions or building the idea of equivalent fractions. And you take one session and you partition it maybe to 8 clips. Every clip would have a transcript associated with it. Every clip would have a brief description about what it's about. It would have who the students are in the clip, or facilitators or researchers. It would have also any work or related metadata that goes along with that, the children's work if that were relevant, or an overhead slide if that were, those days they didn't have whiteboards, they used overhead projectors. So whatever it was that was affiliated with, you could download that as well as download the transcript. And right now we have over 300 of those clips from our study, and we have them in diverse school settings, and we're working harder and harder to get more diverse clips in there from other schools, from other settings. This is available to the world open source. There's no charge, there's no password, you just get right on the repository and you could begin to search. We anticipate that users of our repository are teachers who might be wanting to think about how students are engaged in a particular math activity. When I say students, I mean folks like those of you who come from your classes. Might want to write a report about how a student's learning something or how students engaged in learning, a graduate student, an undergraduate student. People who educate teachers, you might want to look at these data as a pure research. And in that case, you may even want to look at the full video instead of the clips. You might want to, parse it particularly different ways. People who are practitioners, by that I mean people who might write textbooks, or who might be preparing curriculum, and parents. Especially with a lot of the parent moves to do homeschooling, we're finding that parents navigate our website. We can keep track of the people who do this to some extent, but that's another possible group. So, what sort of do we think are some of the affordances of preparing this repository that NSF has generously provided funds for us to do? Well, we are providing ways of showing how children learn from multiple windows, multiple perspectives. Again, the assumption is here that there's not one way to do it. We don't believe in the notion of, here, I'm going to show you how, and this is what you do when you practice, and then you give it back to me. That's not the kind of environment we're talking about. We're talking about, here's a problem. The problem has to be thoughtfully created, engage in it, have students work in group, have them share their ideas, their representations, make these public, be able to go back, revise. It's a different kind of environment, okay? We're talking about an environment that kind of helps stimulate engagement and learning. And there's some research that has been done by in other fields, how collaborative design with computer tools can foster productive collaborative processes, how you can use editing tools to create what they call representational guidance. This is sort of our vision of how some of this may be used. I'm going to talk about this notion of artifact design, that you yourself, the user, will be able to select and annotate video clips. And you can tell your story about what's important in those clips and what do you want to call attention to. And that's significant. So the most recent example that was sent to me by my colleague who's in educational psychology, she's on the learning sciences, one of her students, who's now a doctoral student at City University. What the student did is it traced the argumentation of this group of students over a class session, and looking at the different ways that children's arguments, are framing, making what's visible, what the conditions were, what the assumptions are. These were 9-year-olds doing these arguments, making these arguments. A very beautiful analytic, and I'm sure it'll be up there posted that you could all look at. If you click on the URL that I showed you before, this is the page that you'll get. Okay, this is what you'll be introduced to. And you can see it says teacher, educators, researchers and students, teachers, or just pure research. What we tried to do is give you an example of each of these, of how each of these subpopulations use the tool. So we have different cases that you might want to navigate to follow according to your interests. And if you go on, you'll see these videos circulating and some examples of little clips from these that we've come to give special names to, associated with either the problems or the kind of reasoning. This is one of David's upper and lower bounds. This is a little 9-year-old, does proof by upper lower bound using these rods. I'm just going to show you briefly. I want you to look at David's upper and lower bound. It's absolutely wonderful. But the task was, if I call this blue rod 1, can you find a rod in this set of rods that would have the number name 1/2? I don't know what you know about rods. Do you know something about rods? Have you ever used these before? Right? Do you know what you attend to? There's an attribute of length here. And you could start from the rod that's smallest, the little white rod, and it goes to the rod that's longest, the orange rod, and there are 10 of them, and you could arrange them, and you can see the difference in length. You can imagine a staircase. Following me so far? How many of you are following me? Okay, very good. So, focusing on the attribute of length, this particular, Eric decided that that's what happened in class the day before, the person leading the session, and he tried to argue that there were 2 rods that you can call each 1/2 because they fit on the train of blue. See, the fact is, if you play with this little activity, and I don't have an overhead projector here, but you'll notice that if you have a yellow and purple rod, together they make a train the length of the blue rod. So we said, well, maybe you can call this 1/2, or you can call this 1/2. Now, there's no question that Eric knew what 1/2 is. However, there are not 2 rods in this set, right, that make up a train in length of the blue rod. That was the issue. So it ended up being David coming up to make an argument that in this set there isn't any by creating an upper bound of 2 yellow rods. It's a beautiful video. And what happens when he puts 2 yellow rods? Too long. And he takes 2 purple rods, and what happens when he puts 2 purple rods? Too short. And then he builds a staircase showing there's nothing in between, and he argues there isn't a rod in the set that could be called 1/2 if the blue rod is called 1. A spontaneous kind of argument built by just being engaged in simple problem solving. This is what we're interested in, and this is what we're interested in noting, that students are capable of doing this amazing, amazing kinds of reasoning, given the opportunities and given the tasks. You know, of course, you go on, so the students were then challenged, well, suppose I made a new rod, right? And I took the white rod, cut it in half, and glued it to the purple rod, right? And gave it another name. I don't know. What other name you give it? Give me a name.
Mauve.
Mauve, perfect. Okay? And now mauve, right? I have 2 mauve rods that make a train equal in length to the blue. So now my challenge to you is, does every rod in this set have a rod that if you called it 1 had a number named 1/2? And then another student comes up with the argument, which I thought was amazing, the general argument. You can never have a set of rods so that every rod in the set could have the number named 1/2 if you called it 1, because the smallest rod, he argued there'd always be a smallest rod. Now how about that? We're talking about 9-year-old reasoning, all on video. It's called Allen's Infinity. I wish I had time. If you gave me 3 hours, I'd have a lot more fun here. Maybe another time. But you've got to look at Allen's Infinity. It's just very articulate. He comes, he builds it, he's very clear, and it's just lovely. And those of you who are studying what children do, you know, he starts with his hands in his seat as he's trying to explain what's happened. Then he comes and he takes the rods and he builds it. And you see the different ways they represent ideas, and the way they what's backed with the language they use and the explanations, how they can build a model to support an argument. It's really very exciting. So you see here, that would be one example. I'm just going to tell you what's up here, just to teach you a little bit. So taxicab is something we gave to students in the 12th grade. I don't know if you know about taxicab geometry, but if you can imagine a Cartesian coordinate system, and you can imagine some point, and you can ask how do you get to other points. Well, you can present that problem to the students in such a way that they can notice certain relationships between that problem and others they've done. Taxicab was the last one in our study. But we started working with these children, and you can see from our earlier videos, with one of the greatest tools around. You know what these are called? You should have boxes of these. These are called Unifix cubes. Unifix cubes, right? They're commercially available. And we worked with young children and with these cubes and asked them to do a problem like this. And I'm going to show you a little clip later where they're 9 years old, they're not even using cubes anymore. They've already invented their notation. And they're very articulate with their symbol representation. They naturally transfer from building the model to more sophisticated representations and language. So this is a problem we start them off with when they're actually in the 3rd grade. We tell them they have available, which is something to think about, these Unifix cubes in 2 colors. Let's say blue and yellow. Okay, blue and yellow. You could imagine that we have piles of these. And what we're going to do is we're going to build what I'm calling a tower. That's a tower. Has a chimney on top, stands up. Notice the way it is, has a chimney on top. Can you all see this? So this is a tower of 4 tall. Okay? And we can build other towers 4 tall. There's another tower 4 tall. Right? It's different. If they look alike, even though they're physically made of different objects, we discount it. They have to look different. Okay, these look different to you? So we would call this a 4-tall tower, we would call this a 4-tall tower. The question we ask our little 8-year-olds is the following. How many towers can you build that are 4 tall when you can select from Unifix cubes of 2 colors, yellow and blue? How many 4 tall towers can you build? Now you can't just give me an answer, you have to convince me that you found them. Now that's a very engaging activity for children that age. And I will tell you as a grandmother, it's a very engaging activity for even 3- and 4-year-olds. You should try it sometime, those who are interested in smaller children. I don't think we really know what children can do unless we provide activities like this for them. Have you solved the problem yet? Now mind you, I give this to 8-year-olds, folks. This can't be that hard, right? Okay, do you understand the problem here? Okay, can you imagine all of these there? Do you know how many? What I usually do is I let you talk to each other, and I give you cubes, and I give you a paper and pencil, and I give you a chance to think about it. What's very interesting are the different ways you can justify your solution and the way you can represent, the way you can organize these, the patterns you can find, and how you can organize these patterns. So I'm going to show you a little clip of the children who had already explored building these 5 tall, some explored building them 6 tall, and how we bring them together and sharing their ideas as 9-year-olds about what different ways their ideas. I'm not going to tell you the answer. I'm going to let you think about this. I have learned that when you tell folks the answer, they stop thinking. But I do invite any of you to come up with the answer when you're ready as we move on. Fair enough? You're not allowed to tell. All right, so we have some of that. That problem has the same mathematical structure as this problem in lots of ways. And as well as other problems we've given the students throughout the years. This mathematical structure is what we would call isomorphic. They're structurally equivalent. And for students to be able to spontaneously recognize when that's the case and when that's not the case is a very important mathematical discovery. And what we do is what one of my colleagues from Australia called cognitive theft. We tell them. We don't give them the chance to discover. And you will see the children making these discoveries themselves, and by the way, enjoying it, and saying, shh, 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 don't tell me. They don't want to be told. They want to build and create themselves, and that's very, very exciting. So any of you who are studying or interested in student engagement, are you engaged if someone's just talking at you? I mean, think about how you feel, and think about how the students are that you're working with are. They want to have ownership. They want to express their ideas and pull them together. So you see a lot of that. I showed, this is a wonderful, placing 1/3 on the number line. There are many clips where students were asked to place numbers on the number line. And the mathematical ideas that are generated in doing this are totally amazing. How they do it, how they extend their understanding of improper fraction, how they place 1/3, how they can invent 4/3, and so on and so forth. How can they can discover that fractions have equivalent number names. Lots of activities, lots of connections. Fractions is supposed to be something that children don't like or don't enjoy or don't get to learn well. But you'll see that these children, there's a whole year-long study of these children being engaged in these ideas about fractions that are really, really worth studying. I told you about the rods. This is one of children who are now in high school, who are coming up with the addition rule for Pascal's identity using all formal symbolic notation. So you can see how the representations get more and more sophisticated, more and more elaborate, and how they connect their formal abstract to the specific images that they built as young children, built with these toys and tools and the drawings they made in the representations. It's very exciting. What goes on and on. So maybe enough about that so I don't run out of time.
Who's your student population? Who are you dealing with? Are these students, are these advanced placement type students, or are they students who speak Spanish as a native language? Ooh. Because I can.
Okay, there's a longitudinal study, and then there are cross-sectional studies, okay? So our longitudinal study came from a working class community in New Jersey, where we randomly selected students from children who were randomly, the way the school worked was as follows. There were 2 kindergartens, and the children were randomly put into each kindergarten. When they came into first grade, we went into the first grade, and we chose students to follow, and got the support because we had done professional development in the school from the principal to be able to follow them all through elementary school. And then the students committed to work with us, continued working with us through high school and beyond. This is a population where the students were very good at athletics, and the parents cared about all their accomplishments in athletics. When the best students in the school went to the high school, they barely made C's in those math courses before we came. That's the population we're talking about now. So they were random from this population. Then we extended our study when the children were in 4th grade to go to urban population. Again, this is what would be typical of urban children in a particular school, just randomly picking a group, and again, a privileged population, starting with a group and following them for a few years. The cross-cultural studies didn't go as long. We had one in an informal after-school math program supported by NSF that went 3 years, informal math learning. The cross-sectional studies went 3 years. Then there's a 25-year longitudinal because it couldn't follow all these folks with collecting more and more video and trying to do the analysis. Does that answer your question?
More or less, yes.
You could ask me more come to. I actually have written a chapter about the selection of students that I can put you to if you want more detail.
Yeah.
And give you more explicit.
Because I think that the learning might be culturally bound, and how engaged parents might be in the whole process.
Yeah, these parents were not involved at all, but in our suburban school they were. In our urban school, not at all. 0, 0. They didn't bother us here. They would have been concerned if we did athletics. We couldn't go near that. So yeah, there are of course those differences contextually, and that's no question. I remember going to a parent meeting in the suburban school, and as a young mother came with her fur coat and high heels and said, "Is what you're doing, can you promise that our students are going to get higher SAT scores?" Judy was principal, and she says, "Don't answer that." I'll answer it. And she said, "Yes." I don't know, I couldn't obviously promise that. But this was what parents want. Are our students going to get into these schools? Are they going to get higher scores? That's one population. We didn't have that in the longitudinal study. Any other questions? Okay, so a little bit about these tools. Maybe I'll skip this. You kind of said this already, and I think I'll skip this one. I'd like to go to another screen here. And the reason I want to go to this screen here is because, you see this little icon? It looks like 3 balloons, or an atom, some people say, red, yellow, and blue. Can you see it from way back there? What that means is with this video clip here, and this video clip has a name, it has a description, you can download a transcript for it if you wanted to. But it says with this video clip, there's an associated analytic. Now, how would you get to that video clip? Let me go back again. You would go to that video clip many ways. You can search by taking a grade level. You have some people interested in first grade, you can search grade 1. You can search a math tool. Well, we have a list of tools that we've used, like Unifix cubes or Cuisenaire rods or whatever. There are tools you can search for if you're interested. You can select a math problem. All of our problems are listed, okay, in here in the repository. All the problems we've used throughout all the aspects of the study. You can select a math strand. Now, at all grade levels, you don't have the same option for strands, but we have counting strand. And after counting, we introduced early probability. And after early probability, my colleague Bob Davis was with us and introduced early algebra. You know, counting went throughout, did a little geometry, did pre-calculus, did calculus. So those would be the strands, and counting went more sophisticated throughout, because that was what I was interested in most. So I pushed the counting. We have actually a book out on the counting strand that was published by Springer 2 years ago. So if you're interested in like that. So that's how you can search. You could also search, you see here, you can put in some words, but you can search for what we call analytic. Now, you may have heard the word analytic in other contexts, and for those of you who might, I don't want you to be confused with analytic like in the learning sciences, or analytic as a way of exploring some particular idea. That's the name that the designer of this came up with. She calls it a VMC analytic, and that's the tool I'm going to talk to you about. I'm going to move forward to talk to you about now. So an analytic looks like this, okay? This would be an analytic that was created by one of our graduate students, actually an international student for this, as a project. And as you can see here, the analytic that he's going to tell a story that's going to contain video and narrative. It's going to contain both video and narrative. He's going to pick the essential piece of video he wants in a way that you would cut and paste Word text. You know, you work from a document, you know how to cut and paste text for Word. Well, it's as simple as that. You can go into a video and you start and you stop and you cut. You pick your event. And then you have a way of describing or talking about that event, the space down here. I'm going to actually run one for you hopefully in a little bit. And it'll tell you what you're supposed to be attending to from this author's perspective about that event. Okay? There's also a general description of the event here. It talks about the choose notation. It talks about the problem that the student referred to early on, the tower problem. And it goes on to describe sort of the history that this particular student wants to be able to describe to lead to the event of what's called locating Pascal's identity. Do you all know what Pascal's identity is? Pascal's identity? Good, yeah, the triangles. You know what that looks like? When I help people, you ever see the triangle? It starts with a 1, then you have 1, 2, 1, 1, 3, 3, 1. Does that sound familiar? That's kind of interesting, because I have another analytic that that's what I'm going to show you of Stephanie, who's making sense of the binomial. You hear binomial, a plus b quantity squared, a plus b quantity cubed, a plus b raised to the nth power. How Stephanie's making sense of that, relating it to her tower building, relating it to some other problems, and relating it to Pascal's identity. And this is over a series of events. Look at the multi-connections that are being made here. Think of the richness of these connections. I mean, these are not math major students. These are just, you know, kids who are engaged in the math and are noticing things. They're making connections. They're relating. And so if you wanted to tell a story, either over time or over one particular period, or attend to some kind of thing that's going on that interests you for some reason, you could make an analytic. Very important for teacher educators, right? If they wanted to make a point to their class, right, and show them something and illustrate something with video, you can do that. You can create it.
So how would you define an analytic?
How would I define? Well, this is a VMC analytic. I should have written VMC analytic. So it would be a video narrative. That would probably be good enough for you now. A video. There's a more technical definition, and there's a technical paper that I'll show you at the end, that was written all about the VMC analytic. Really, those who are interested in it, the way it's designed and the way it was built and the system and all, that was written by Grace and some of us in relationship to this study. So that, but right now it's a narrative with video as part of the narrative. And so you have text, you have video. Get the idea? So, moving on. I really hope that if if you're really liking any of these ideas, that you actually go on the website and start to explore for yourself on the clips. Where we are right now is thinking about access to full videos. And also where we are right now is making analytics from the full videos. And the reason that the interest has shifted is, one, because it's more cost effective. It's very expensive to put in all those clips, and that's number one. It's easier to just put in one full video. But there's also data that have not been analyzed in detail. And it's these data that our doctoral students and some of our master students for projects are doing for their projects and dissertations, as well as other researchers, or folks who are writing chapters or books or whatever. They want the full videos, they want access for their writing. And the way that we are doing this is by releasing full videos and setting up the tool to make the analytics from full videos in our high-speed Internet 2 Genie laboratory. Now, you have very good high speed here. You were very fortunate. Those of your students don't know it, you were very fortunate. Which means you'd probably be able to download the full videos and work from here if you wanted to. If you want to. It's slow in a lot of places. And it's getting better. So we're really optimistic that working with full videos is the future. But I have students, for instance, who are doing projects that they're producing sets of analytics to really follow particular research questions that they've posed. And they're exploring and investigating. So they're not just backing it with transcript now, they're backing it with video analytics and transcript of those pieces. So that's become quite popular.
That's a quick question.
Sure.
Can these then be referenced, either in a paper or
Sure.
in a document, so that
Yes.
you click on it? See, to me, that's
Yes,
the
you can
value in some of this.
You can actually, everything here has a permanent URL. So you do an analytic, and you probably want to publish, you submit it, so we look at it and say, yeah, this is great, publish it, or you might find a typo you might want to change or whatever, So a couple people look at it. You get it published, that's exciting. It gets a permanent URL. You can take that permanent URL and you could give it a marker that's a shorter one, whatever you want to call it, and you actually put it in your paper. So we're doing it in special editions of journals that we're doing now. We're doing it in book writing, new book writing. Students are doing it in their dissertations.
And are you focusing merely on math? Not merely. Are you focusing on math or math and science, or is this across the disciplines? Or
this collection was a collection that came about over many years as part of looking at how mathematical ideas and ways of reasoning are built. My colleagues in other areas are using the collection to look at more general ideas, learning, collaboration, teacher questioning, how groups work. And those bigger questions, the fact that it's mathematics is nice, but it could be done in other places. No, we don't have anything. We don't have videos from other projects except the ones. This is developed over our long-term studies associated with mathematical learning. I mean, it'd be nice to have it in all areas. And I think there are other people who have different kinds of collections in other places. I don't know how accessible or not they're open source, but I think they're there. Does that answer your question? Mm-hmm. Okay, so it's the high-speed Internet Genie Lab that is our hope. And what we are doing now with funding from the National Science Foundation is to study how people do this. And an example of a collaboration over the Genie Network, we can do it here. Suppose you wanted to make an analytic. We can connect you to our lab. We could have a session, and we can make an analytic together. Okay, we could have it, as we did with the University of Kentucky. So they decided they wanted to make an analytic, and so we were leading the analytic, and we used the repository there. We had a collaboration. It was in real time, and that's how they learned how to make it. I mean, I know you could probably, some of you just go play with it, you'd be able to do it yourselves pretty easily. We have a little instruction manual, and I bet you if you tried it and had the instruction manual, probably you'll have questions you'll ask us, and then you tell us what to fix our manual. That'd be great. That's how we learn too. So it's not that difficult. So I'm going to shift gears a little bit. I've talked a little bit about the collection. I haven't shown you a video yet. I've talked a little bit about the VMC. We've done some design research. And while we're building the VMC, we were also supported by NSF to do design research about teachers learning from videos. And we did this in 2 strands. We did this in accounting and the rational numbers strand. And we used the model that we had success with prior to this funding, which I call modified lesson study. And I'll briefly describe the model. You earlier heard the model, but it goes like this. We have cycles of interventions with our participants, either folks like you, if you were at our school, or it would be practicing teachers. So we have 2 populations, pre-service, elementary, secondary, practicing, they work middle school. And in our cycles of of lesson study, we give you all together working in groups. We'd have you start maybe by working on this problem. We'd give you the tools. We'd ask you to write up your solution and share it. Did anyone work this out yet? Okay, I'm glad you're paying attention to my talk. So you'd work on the problem,
16.
and you'd be asked to think about what the strategies you used, you know, and how you represented, how other people did it. Then we show you videos of the children working on exactly the same problem. And that's very powerful, you'll see, because after you thought about the problem, you see what the students do, and you say, my gosh, they did it faster.
Can I ask one more question?
Yes.
I'm interested in digital storytelling and examining digital stories for reflection and for learning.
That's cool.
So this is
Yeah, that's a digital story.
It's a digital
That's
story
great.
because it's got a problem. It's got it's got a background, a problem, a solution. So it's told in a story format.
Yes.
But then I guess forgot exactly what I was going to ask. But if you have students make their own videos, do students make their own videos, or are you looking at videos made by others of the students?
All the videos come from funded projects that I have had over the years.
Okay, but the students, the little 9 and 10-year-olds, they don't make their own videos.
They're just participating.
That's what.
I bet you they could, though. It's a good idea. Right.
Yeah, that's.
I'm
what
sure
we're
they
doing.
could, actually. Okay, so our model here is you work on the problem, you share your solution, you discuss it, you watch the children, you share the solution and discuss it. You look and compare strategies, what the students did, you notice things that maybe, you picked up some things when you shared with each other, right? Maybe other groups worked differently than yours and had a different way of representing their ideas. So you picked up a lot of ideas already, then you study videos and you're picking up more ideas. The component that was with the in-service teachers, then they did it in their own classroom with their own students. They studied their own students' work. They analyzed their work and brought back for sharing examples of stuff that impressed them that their students did, stuff they didn't understand, or things that were confusing, or things that surprised them. These are the sort of the 3 categories. And then there's more conversation and engagement about that, and that goes through different cycles of problem solving. That's sort of our model. So when I talk about a modified lesson study, that's what we're talking about, model. And that was the nature of the intervention, except for the last part of taking it in the classroom was for our pre-service teachers. In-service teachers, they took it in their classroom. In each classroom, the time implementation was different, depending upon how long we could get in there to do the implementation. So we went to our secondary methods course on math majors. They said you could be in here 2.5 weeks, which means like 5 sessions. If you go to the elementary methods course, they'll give you 3.5 weeks. You get the idea. It depends on how much a person lets you. So we know there was variability in time. That was a factor that we could not control. And we were interested in studying the extent to which the study participants noticed details in students' mathematical reasoning before and after the intervention. So what did we start? We gave them a video to look at, and we gave them also the transcript, and we asked them to let us know what are the arguments that were there that the students were given, what was convincing. So gave them the same thing at the end. We also had comparison classes where there wasn't an intervention. So with elementary, we had elementary, with secondary, we had secondary, and so forth. So we had comparison classes and experimental classes. And our hypothesis was no difference in growth between the two. But that's not what we found. So here, you can look at our participant groups here. We had elementary, they were K to 5. Those who were studying to be teachers in grades K to 5. Then we had the in-service teachers, and they're called K to 8, but they were really middle school teachers mostly, okay? That's how they certified them in our state. And then we had secondary, these were math majors, pre-service teachers. And we had experimental and comparison groups as indicated there. Because the assessment was open-ended, we had to come up with a very detailed rubric to code the open-ended responses. That was a lot of work. We had to get the arguments broken down into its features, and the main arguments that we were looking for here were 2 case arguments that were exhaustive cases. Like, for example, here, I can tell you how many that have no yellow, how many exactly 1 yellow. Can you imagine that? 1 yellow in each position, right? How many exactly? You get the idea? 2 yellow, 3 and 4, and you can look at other relationships here. So that would be an example of a case argument where you have looked at non-overlapping cases and you've looked at exhaustive cases. And it was an inductive argument where you can argue something like this, which children argue. Well, if I were building them 1 tool, I can make how many? How do you know that? Because the given is 2 colors, and you see it, right? You're given 2 colors, and that's why you have 2 choices, right? If I got 3 colors, then so they come up with that argument. But if I started with a yellow on the bottom, what could I do with the yellow on the bottom? Well, I could put another yellow on top of it, right? Or with the yellow on the bottom, I could put a blue on top of it, right? Same thing with blue. If I started with blue on the bottom, I could either put a blue or a blue. And they use that argument to continue to show an inductive kind of reasoning that would have been as compared to a case reasoning. Now, children are not as elegant in their language, and they may not start always at 1 tool. They could start at 2 tool. You know, children don't talk like a textbook. You all noticed that, right? And especially if they're doing it the first time, their language gets better over time. Okay, so this was an issue. So we dealt with the different arguments, and we had inter-rater reliability in each case with a lot of work to be more than 90%. The data was analyzed using a logistics regression model. If you have any questions about that, you can talk to my husband after this. But I'll tell you a little bit about what we found. So we've looked at the growth rate of the experimental groups and that of the comparison groups. And the growth rate of the experimental subgroups, elementary, secondary, and in-service, mostly middle school, exceeded that of the comparison group at significant levels that varied from 0.05 to 0.0001, so very significant. What's really interesting, if you look at the data here, is that there was no growth for the comparison groups. So they were pooled together with the sample size. And I think if you pull them all together, I think it was like 4%. It was very insignificant. So in comparison, when you looked at the growth rate for these other groups, look at them. The experimental K to 8, 0.5185, secondary, pre-service, and then the K to 5. So this is the in-service teacher group. The ones that actually had an opportunity to try it in their classrooms. Look at their growth rate as compared to the pre-service, those who don't really have a chance to work with students, don't have a chance to try the activities in their classroom. It's different, isn't it? You'd expect that. And so if you look at this with the terms of odds, you get to look at the confidence intervals for the odds ratio for the lower and the upper confidence level for these, and it's really very, very impressive. Okay. Go ahead, Jim. You were going to say.
Well, I just want to comment. When you get back to the line. The in-service teachers, where the growth rate is 0.5185, that means that 51.85% grew on this task. Right?
So it's very encouraging that everyone grew. I think that's encouraging. Obviously, there's more room for growth. Right? I mean, personally, I want to see more room for growth. I would have been very disappointed if there was no growth. I could understand the difference in growth, right, from the data. It kind of makes sense. But, you know, you can talk about why you might want to have more growth. And, well, how long do we do this? You know, how long was the intervention? What can you do in 2.5 weeks? What can you do in 3 weeks? Interesting to me, even the math majors, right? These are the best of our lot. They come into our program with BB plus averages. They're the best of our lot. They still had room for growing. They might have known the math, but could they recognize it in when they see children making these arguments? That's the issue. There's a lot of work to be done.
Yeah, but they didn't have teaching experience.
No. So. Went away.
Let's see.
Okay. Well, what I really would like to do is, I don't have only a couple of minutes. I'd like to show a brief video and give you an example of what's going on with the kids. But there's promise here, and I think if you want a full paper, I can show you a full paper. I also would like to show you, I promised the young ladies over there that I'd show them these 2 little girls working on this task in grade 3. It's a very short little video. This is Stephanie and Dana. And they're part of
Dana is 9. Okay. Look, just Dana, first I want you to figure out. We may get different answers. Look.
They're looking at
You've got white, and white. That's 3. Right? Then yellow, and yellow. That's 3. That's 6. And then blue, and blue. That's 9. They all, it's 5, 6. That's 6. And then we add.
That was in technology 25 years ago. See how we had to watch.
So Dana, your calculations were wrong. It was 9. Now Dana, for the second problem, I get to write, okay? Because if you can get 3 from each one of you, you did it. It's 9. It's 9. How did you get 9? Well, just we brochured, and since each one of them can go to 3 pairs of jeans, 3, 6, 9.
Oh, 3, 6, 9.
Because there's 3 pairs of shirts and 3 pairs of jeans. If each shirt could go to 3 pairs, it would be 3, 6, 9. 3 is 1 top, 3 is 9.
Oh, I see. What if you make 4 pairs of jeans? What do you think would happen? Think about it. You don't have to do that.
You would have to just do like 4, like 3, 4, like 3, 6, 9, 12. It would be 12. 3, 6, 9, 12. You think so? Or convinced you?
So it's fun to watch these 2 over the years. It really is. And I don't know if you have a chance to see what more. I know some of you have to leave and you can, but I want to show you this as a goodbye one because they had worked on Tower's problem, and now it wasn't about, it was a kind of a group thing to see.
I found it like that.
Sharing ideas.
I drew my lines, and then I went red, 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 blue, 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 red, blue, red, blue, 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 red, 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 blue, red, blue, red, blue, red, red.
So what I'm hearing you say is that you're just Guessing.
You believe there's 8, but you say guessing. Now, why does that sound like guessing?
Because what if you could make more?
Okay, this is the 3 high, right? And you're convinced you can make 8.
Yep.
I'm convinced I can make 8.
But could you convince her?
So, Shell? Him?
No, her.
Her? Yeah. Alright. I've done this before. Okay.
Take another piece of paper if you want to. You got to convince me there are 8 and only 8, and no more or fewer.
Alright, first you have without any blues, which is red, red, red.
Okay. No blues.
Then you have with 1 blue.
Okay.
Blue, red, red,
Mm-hmm.
or red, blue, red, or red, red, blue.
Anything else?
And you would do the same pattern for it.
No, not with the blue.
You
Not with
would
one
do
blue.
you would do it with the 1 red and 2 blues.
alternate,
You would do
like-
it the other way
I want you to
around.
let her finish. That's what
Yes.
you would do. You would alternate. Let's see what Stephanie does. Maybe she's
Well,
Same
there's
thing.
no, there's no more of these
Okay.
because if you had to go down another one, you'd have to have another block on the bottom.
Okay.
Yep.
Okay.
Then you have with 3 blue. Well, not with 3 blues. I'll go like this.
You have no blues, and now you have exactly 1 blue.
Okay. Now you have exactly 2 blue. You can put blue, blue, red. You can put red, blue, and blue.
You could put blue, red, and blue. You could put
Yeah, but that's not what I'm doing. I'm doing it so that they're stuck together.
There should be one, you could do 1 with 1 red, then you can make it up and there's 1 with 2 reds, and then there's 1 with 3 reds. And,
but see, you did that same
see,
thing, but
there's all
blue.
reds, and then there's 3 reds, 2 reds. There should be 1 with 1 red, and then you change it to blue.
Well, that's not how I do it.
Let's hear how Steph. We'll hear that other way. That's interesting. Okay. Now, so what you've done so far is
1 blue, 2 blue.
no blues,
1 blue, 2 blue.
1 blue, and 2 blues. But Millen just said you don't have all 2 blues, and you said that's why is that?
All right, so show me another 2 blue with them stuck together, because that's what I'm doing.
That makes sense.
Okay. So now we're
But if you just had 2 blues and they weren't stuck together, you could
But
put
that's what I'm doing. I'm doing the blues stuck together.
okay.
Then we have 3 blues, which you can only make 1 of. Then you want 2 blues stuck apart, or not stuck apart, took apart.
Separated?
Yeah, separated. And you can go blue, red, blue.
This goes on. This video was shown by Bob Davis at the retirement of Andy Gleason. I don't know if those of you know who he is, but he was chair of the math department at Harvard. Andy Gleason never had a doctorate. Apparently no one was smart enough to be his advisor, I'm told. And they had a couple-day celebration when he was retiring. And we had just made this. This is like about a 90-minute video. It's really worth seeing the whole one. Because after a while they're asked, how many can you do when you're 10 tall? She says, well, I could do that. That's 1,024. I've already done it. I mean, this gets better and better if you look at it. But it apparently got a lot of ovations at Andy Gleason's retirement from Harvard at that party. Bob Davis called me on the phone and said, they really liked that video, which was fun. Anyway, there's lots more. I know you have to go. I think I've exceeded my time, and I think you're, is that right? Did I exceed my time? Do I have more time? Oh, I can show you another one. That's so exciting. So I'd like to show you then an analytic. Would you like to see an analytic? Did you like the Stephanie one? This is they're 9th graders. Now, mind you, they had built them with these Unifix cubes up to 5, 6 tall. Didn't want them. We asked them if they wanted them. They're using notation now, just naturally. It's kind of cool. We don't see Millen's argument in there. He's the one who builds the inductive argument. We just made it really brief because of time. So let's. I love Alan's Infinity. You would love that one. And I could show. This is Bob Davis, my colleague, who we have some wonderful algebra videos of him. Okay, Stephanie again. Okay.
hairdo.
She's in the 8th grade. And this is Stephanie. I'm going to try to